This is Self-Directed Research. Our hosts, James and Amos, get hyped about different topics and take turns each week presenting their ideas to each other. You can check out the website, YouTube, or Spotify to watch this episode's presentation, and visit sdr-podcast.com/episodes for presentations, videos, show notes, and transcripts. New episodes are published every Wednesday. This episode is brought to you by Code Crafters. Check out the link in our show notes or listen at the end for more information. But first, James brings you 75 slides about a different Serde.
James, what do you have for us today?
Today's a different Serde. We've talked a lot about Serde things, and now it's time to look a little deeper than Postcard and look at Serde itself. A surprising number of people that I talk to don't realize that Serde comes from the name serialize and deserialize, and also everyone says it different. I've heard Serde, I've heard Serde, I say Serde, but that's one of those things that I'm sure people will let us know in the comment that they have opinions.
I say Serde because I'm French, and also because that way my joke Serde alternative works. But I don't know if I'm allowed to bring it up because it's your episode, James.
Serde is a quick recap. To understand why I'm proposing something different, it's good to understand what I'm talking about. So Serde has two main parts. It's got a front end that thinks about Rust types, so it's firmly in the world of Rust data structures. And it's got a back end that thinks about the wire format. This is your JSON, your TOML, your whatever collection of bytes you'd like to represent your stuff when you write it to a file or send it over the wire or anything like that. And everyone uses Serde. That's a really good thing because Serde is much better than the alternative of casting your structs to arrays of bytes and then mem-copying those to the wire, which is a serious thing that unserious people do. Postcard uses Serde. So Postcard's built on top of Serde. Because it has this flexibility between the front end and the back end, I can define a very compact binary format, and Serde is written in a very good way that works with embedded systems, so even little microcontrollers can use Serde the same way that big servers use Serde, so it's wonderful. Despite the whole thing that I'm going to say in this presentation, you should keep using Serde. Serde is a very good tool that I like, despite having messed around with other things. Today, you should absolutely keep using Serde. But Serde has some problems, and we're going to talk about those a little bit.
Oh boy.
Because I am who I am, sometimes I wonder whether I could do it better. Maybe not for the general case, but at least for what Postcard needs. Because Postcard is a very small, simple format, and it doesn't need necessarily all the power of what every single possible format could need, like Serde has to support for all of the formats that it has to support.
Okay, I'm going to make this harder on you by interrupting you because it's my job as a co-host. You said because I am who I am, and I recently had a DSM party at my house. I don't know if you know what it is. It's where you read the DSM 3, 4, and 5 of the Diagnosis Manual for Mental Disorders.
Oh, okay. Yeah.
And it's very interesting to see that you only have a thing if it's a problem for others. So as long as it only bothers you, you're not clinically anything.
Yeah, there's some delayed sleep phase disorder or something like that, and it was weird to read Wikipedia and I go, they're describing my life. But yeah, I think I kind of know what you're getting at. But how Serde works, so I mentioned that it's got a front end and a back end. Serde has a data model, so it's got essentially a limited palette of types that it thinks in. The palette's not so limited, there's 29 different types. This covers everything from primitive integer types or primitive other numeric types, arrays like string slices, arrays of T, byte slices, things like that, composite types like structs and tuple, so a type that's made up of other types, and discriminated types like enum and their variants and all the different flavors of enums that you can have. So these all collectively make up the 29 data types that Serde thinks in. I mentioned that there's two parts. The front end's job is to turn Rust types into data model types, or for deserialization the other way around, data model types into Rust types. And the back end takes those array of strings and turns them into bytes on the wire. For JSON, that's text. For Postcard, that's a length prefix and then just the raw UTF-8 bytes on the wire. But that's the two-step process. We kind of have that even middle meeting point from whatever type you want to whatever format you want. There's sort of always that middle step of picking which data model type you're choosing to represent that data as. The other way that Serde works is by using what's called the visitor pattern. Because there's sort of this two moving part thing, you kind of have to figure out, well, if I was making it totally generic, I'd have to be generic over the type and the serializer or what. And Serde chooses a programming pattern that's popular in other languages. I know I've seen it in C++ and Java, I think. But the visitor pattern, which is essentially you hand the type the serializer, and it derives that pattern. These types are given a serializer, and each of those data model types have a serializing method. So the type can say, okay, I've got this field that's an integer, or let's say specifically a U8. I'm going to call .serialize U8 on it, and I'm going to give it the U8, and then it will turn that into the bytes on the wire. And so the type is the one that drives the visitor, and then the data format is the one that says, this is how I turn a U8 into whatever representation makes sense in JSON or TOML or anything like that. So you would call your .serialize U8, .serialize stir, and you're handing it the instance of that type that Serde natively thinks in. So this drives the backend. Postcard says, I'm being told to serialize a U8. I will put that on the wire. I'm being told to serialize a stir. I'm going to put that on the wire. It doesn't really think about the context of what's going on. It just says, I've been told to do this, bleh, data goes out on the wire, or I've been told to retrieve a U8 or a stir from the wire. I will try and consume up some bytes and turn it into a stir or a U8 or whatever. Now, this visitor driver code is usually derived. You usually don't have to write this, even for other types. You just throw a derived serialize on there, and a procedural macro goes in and generates, okay, I have 7 fields. The first field is this. Do this, do this, do this, do this. And it expands out into essentially driving that visitor at all points. So you can take a type like this, a struct that has 2 fields, put derived serialize on it, and you get a relatively lot more code, which runs this process. We're implementing serialize for PWM error. It starts a struct, it does each field of the struct, and then it ends a struct. Postcard doesn't care about the start and the end, but if you were in JSON, you might want to indent and start a new curly brace and then do the fields, but it's got the ability to handle all of those cases.
I cannot help but notice on this slide, the third argument to serialize struct is false as usize +1 +1.
Yeah.
I'm sure there's a reason for it, but it's a proc macro. Why can't it just say 2?
I have no idea. It's probably one of those who am I to question DTOLNE when it comes to writing proc macros? These are arcane that I do not want to know about.
I will look into this. I want to look into this.
Yeah. The other thing is Serde also, I think, supports all the way back to Rust 2015 or whatever. So sometimes it does some weird anachronistic things because it has to work for all versions of Rust and things like that.
Granted, but I'm pretty sure we've had integer literals for a while. So 0 has been there the whole time. That I'm pretty curious what it's there for.
That's a whole other episode, I guess. And there are some problems with deriving all of that code other than just false as integer for some reason. So the main problem is that it generates a lot of code. It can generate a sometimes double-digit multiple of the input source that you are giving it. This is a picture of a Blue Sky post. This is from a customer project where it's a little bit silly, and I think they've fixed it since then, but they have 50,000 lines of code in one crate of raw source code. If you just run Tokay on the project, you get about 50,000 lines. If you do the expansion of that, so you run it through cargo expand and then count the expanded lines, it's over 200,000 lines of code. And one of the file that is basically just type definitions was a little over 1,000 lines of code, and after expansion of just that one file, became 22,000 lines of code. There's a lot going on there, but a lot of code is a lot of code.
Yeah, and the thing is, it's all generic code as well. So it's going to be instantiated using a serializer or a deserializer implementation. So that's just the template in C++ parlance, I guess.
Yeah, and this has measurable impact. I mean, the reason I was looking at this is because it took 40 seconds to do a build of that one crate. And this was their main binary crate. So every time they touched it, it would take 40 seconds to rebuild, which was painful.
Yeah.
And like you were saying, there's a lot of monomorphization and inlining. This isn't necessarily Serde's fault, but Rust, like you said, generics are templates, basically, so it will stamp out a version of this. If you have multiple serializers, it will stamp out a version of each of these that are used. And when it comes to the optimizer, we will inline a lot of this, which means some of those instantiated copies will end up being one very large function, and then you'll have multiple versions of that function because they get inlined in different places. And so it can end up taking a fair amount of compilation and optimization time, but then end up as a lot of code in your binary as well.
Yeah, that's what I was thinking when you were presenting the visitor pattern and how you have separate methods for separate types. I was thinking because in my Serde alternative, which it's not the topic of today's presentation, believe it or not, I just have an enum. But then if you have an enum, you have dynamic dispatch. You have to match on the discriminant of the enum and then know if it's a string, if it's a number, if it's whatever. Also, it's inefficient for a bunch of other reasons. But the reason Serde has methods per type is that it can inline everything. There's no dynamic dispatch at all. It all gets compiled down to just compact code. And you pay for that in compile times. And I think a lot of the times when people complain about Rust compile times, they're actually complaining about Serde generic instantiations.
It's one of those things, it's a useful tool. And that's one of those hard problems of in isolation of just a couple types, it would be fine. But that customer project that I was talking about, they have hundreds of types that each have many dependencies that all generate code. And to be fair, on one hand, it's a problem of success, of it has gotten so successful and it's so widely used, it becomes the easiest thing to point at. I don't want to point too hard because it is a good tool, but it gets creaky at a certain size.
Of course, now that I think about all this, if you were to like take types and put 100 in different crates and then export non-generic functions, then you could actually cache some of it. The problem is that you have all the types in one crate in 50,000 lines of code. I'm just realizing that I've been working for 6 months on an alternative when actually there was a compiler hack that could have done everything. Don't mind me. I'll be over there.
Okay. Another problem is that the visitor pattern is recursive. When you call serialize on a field that is being serialized, you're then calling that serialize method, which then if it has children, calls those, which calls those, which calls those, which is not always necessarily a problem. It's a nice way of writing the code because every struct is essentially isolated to its world. And when you have to go into another world, like for serializing one of your children, you just call a single serialize method of it. So it makes it locally very simple. But when you have very deeply nested types or things like that, the call chain can get somewhat deep on this. And especially the more functions you call, you're just eating up stack frames and usually returning things back down those stack frames, which can add up to a little bit of cost.
Did you actually run into that in embedded, or did you run into the opposite problem where like the structure is not that deep, but the stack that you have is smaller than you're used to on desktop, for example?
It can, especially for deserialization, data is returned by value. And sometimes because we don't have a heap vector, we will use stack allocated vectors where you say, okay, here's a bounded vector with room for 32 items. And when you return that deserialization step by value, even if you only deserialized one item, if it's a fixed size collection, essentially you have the capacity for all 32, you're going to return that by value down the stack frame, which means you've created that whole 32 item vec in one function, and then returning it by value means you memcopy it back to the caller frame, essentially. And this is one of those things that LLVM can optimize sometimes, but RVO is not a guaranteed optimization.
Yeah, RVO is return value optimization?
Yeah, so there's RVO, which is return value optimization, and NRVO, which is named return value optimization. And the idea is that essentially you make space in the caller and use that in the callee so that when it's populating that, it's actually populating it to the destination. And when you return, you actually end up just returning nothing, and the data is already there, is the transform you're kind of going for there.
This might be where you're driving, but as far as I know, Serde has a deserialize in place. Like a lot of Rust APIs include an in place version because of the lack of guaranteed RVO and NRVO. Is that?
I haven't run into it.
It's dog hidden is the fun thing.
Then, yeah.
So I only found out about it because I've been snooping around the source code.
I haven't run into that. I might have to poke into that.
Yeah, you should.
And for Postcard, it has more flexibility than we need. The visitor drivers here have the capability. So for example, in JSON, the fields don't always have to be in the same order. You might order them differently. Like JavaScript might order the fields in one way and Rust orders it in another way, which means for certain types, you have to be able to visit each thing's out of order, fill them in, and still end up with the ones that you need. Postcard does not do that. It says they are always in the lexical order. Tuples are always, 0 to whatever. Structs are always top to bottom. And then when you get into attributes like rename or skip serializing if or skip deserializing if, there's hooks at certain point where the visitor can change behavior or even flatten things, which one makes Postcard very upset because it doesn't like that. And two, it's just flexibility that you don't necessarily need in all cases. I'm sure there are people who love those functionalities, but at least for me and for Postcard, I don't want it.
Wait, so are you paying for code that is able to handle fields out of order, even though that never happens with Postcard? So you get visited with key value pairs, I would imagine, and then you can do whatever you want. And you could, in the implementation, assume that they're in the expected order. I don't know.
I think it's one of those things that if it does exist, it's almost certainly optimized out.
Right.
I believe that Serde has the latitude for that, but I don't necessarily think that we're paying extra for that in Postcard by not using it. There's certain attributes that do trigger that to happen, and these are the ones that confuse Postcard, because Postcard doesn't keep track of what you visited and not visited at each step. So if you try and do things out of order, it just grabs wrong fields in the wrong order. I'd have to check. The answer is I don't know.
Got it.
This is a fairly reasonable way to approach the problem of serialization. You break it down into each type, you locally figure out how to handle each type, and then you handle it. And then you do it sort of recursively. It's like a very straightforward, well thought out way to approach this problem. So how do we even think about other ways of approaching this problem? Well, I spent some time looking into a weird, archaic programming language called Forth, and it broke my brain a little bit. Now I'm going to talk a little bit about Postcard-forth, which is an experiment I did a while back that had some interesting results. It's not ready to use by any sort of the imagination. I'm going to slap a big old experimental sticker on that because it's gross, but it's an interesting research project. How Postcard-forth works is a little different. We do keep mostly the same data model. We say, look, there's a limited palette of types that you can convert to and from. That's sort of our bridge from Rust world into the wire world. And Postcard really already has this because I only define the 29 different things you can put on the wire in Postcard format. So we're kind of already there. Mostly keep the same data model. Skipping ahead a little bit, we would have a much simpler derived macro. So rather than generating that visitor pattern, which is going to generate functions for us that are going to drive that serialization or deserialization process, we only generate a list of field offsets and function pointers for functions that know how to serialize or deserialize that data. So for a type that looks like this, outer that has 3 fields, one of them being inner, a struct inner that has 2 fields, some integers, some strings, some vex, things like that. Instead of something vaguely like this from Serde, where we'd have outer, which is going to call serialize U32, then serialize stir, then serialize on the inner struct, which is going to call you know what I mean. Instead of implementing the trait like this, instead we generate something sort of like this, which is a constant array, and each element of the array is a tuple of a usize and a function pointer. The function pointer takes a const pointer to the unit type, so basically a type erased pointer, and a mutable reference to an output stream of bytes. So what this is trying to say is we have an array of things. We have the offset from the base of the struct to this specific field, and then the function that's going to handle that.
I have several comments. First, if you're listening to this, every time James says this, he is actually pointing at a screen. You could be having this on your screen. You can find the slides at sdr-podcast.com/episodes if you want to, and then find the episodes we're talking about, and then you can have the slide deck on there. Second, I think it's hilarious because I'm looking at the slides that James went the exact opposite direction that I went with the slides, where he's using a pixel font and I went with a pretty, what did I get? Atkinson hyperlegible. So this is like polar opposite typographic choices. Thirdly, James, isn't that FFI unsafe to have a const pointer to the unit tuple?
What do you mean FFI unsafe?
It probably doesn't matter, actually, because this is staying inside Rust. This is a C pattern. In C, when you have an API to do something, there's always a void pointer.
Yeah, this is void star. This is Rust void star. Yeah.
This is void star, pointer, context, whatever. You'll see that in all C-style APIs. So seeing it here brings me back. The trauma, it's all coming back to me.
Oh, yeah. This is explicitly type erased pointers to data.
But it's not exactly the same thing. Like, I think if you put that in an extern C function, the Rusty will yell at you saying, like, it's not guaranteed that this is actually the same size as a void pointer or whatever.
You can't pass a tuple because C doesn't have a concept of zero size types, and C++ doesn't either. But a pointer to a zero size type is still allowed. That's how I believe opaque type works in C, is that it's a size that the compiler does not know about. And that's essentially how unsized works in C, because it doesn't have a proper concept of unsized.
Right.
But I could be wrong. I think you get the point that I'm going for, like, void star pointer here.
Sure. My other question was, isn't offset off something that was just stabilized?
Offset of enums is stabilizing. Offset of has been there for a while, but probably this year or last year or something like that.
Something like this was in a recent changelog.
Yeah.
I forget which.
They're still working on it because offset of enums is not totally stable yet. And we'll get to that because there's an RFC I'm going to mention. But offset of itself is stable at this point.
Also, I'm looking at the slide, which again, go to sdr-podcast.com/episodes to find out. But does Serde slice U8 turbofish like Q8, which gives you the instantiated version of that, the monomorphized version of that function, and that's a thin function pointer.
Yes, exactly. You can monomorphize generic functions and not put the parentheses at the end of them. So the turbofish actually does the instantiation of that specific version. So it is no longer a generic function. It is a specifically typed function pointer at this point. You use this a lot in Waker dispatch tables, or what are they called? The V table that you have to create for async functions.
Right, for futures. Yeah. This makes a terrifying amount of sense, but I don't think I would have thought about it. You just blew my mind, James.
Good. So we end up with this array, and even though we're still generating, the length isn't so different, especially for these simple ones. The neat part about this is the offset is a usize, so it's one word, 4 or 8 bytes, depending on what platform you are. A thin function pointer is one word. So for those two fields, that is 8, 16, 32 bytes for that, plus it's a slice, so maybe another one and a pointer or something in there. Something on the order of a handful of words. And same for outer. So code is usually pretty dense, but I'd probably bet that this is maybe a little shorter than even the generated optimized code, particularly before you've inlined it and stuff. And we're just working with data. It is a constant value that doesn't get used unless it gets used. It's not even code that has been generated at this point. I've already talked about doing tricky things with macros and const functions to merge arrays of things so that you end up with one array. So maybe for that outer one, we don't even have that call to the offsets of the parent fields and then calling into some function that handles the inner. We just splat the entire list into one list, and all of a sudden we have the entire makeup of this. And even though these are repr Rust types, offset of works with them. So you can take the base of one struct and add the offset to that field, and then add offsets to the subfield and splat it and get an entirely correct offset of that subfield.
James, token listener here. First of all, which context did you learn the word splat in? Because I know what you mean. I'm thinking of JavaScript.
That's a Python thing. Yeah, splatting is when you had an array of 3 things. If you were to splat it in Python, that would be then passing the function 3 arguments instead of an array of 3 elements.
So because this is a presentation about Rust and Serde, it's the equivalent of Serde flatten, right?
Sort of, except for we're not flattening the types necessarily. We've just merged the child list with the parent list so that the parent list it's a flattening operation. Same kind of thing. We are flattening here for sure.
Cool. And then the other question, you offhandedly mentioned it was repr Rust. So that's REPR parenthesis Rust with a capital for some reason. And we have repr C as well, and we have other ones that I forget.
Crabby.
What that does is it defines the layout of structs, if I'm correct. It defines the API. So if you have something that's repr C, that is well defined. That is not going to change. That is what we use for FFI, foreign function interface. But repr Rust can change from one, even across 2 compiles. There's no guarantees that it will stay the same.
Yeah, it means you're not allowed to know it. At least are the rules of repr Rust. So you can't rely on that. But using the offset of macro says, whatever the compiler thinks this layout is, use that offset. It's out of my hands. What we're trying to do here is instead of using the visitor pattern, we're turning Serde into a stack machine. And this is where we get back to Forth. Forth is an interpreted programming language that is very simple. It has very few primitives. It has no local data. The only local data is the stack. And the way functions are defined is essentially as arrays of other functions. So you name an array of function calls, and that becomes a new function. And you don't have to worry about passing data to functions because there is no way to pass data to functions. There is only the stack. And so it ends up looking a lot like recursion, but you sort of manage it by the VM itself rather than the compiler creating this machine for you. So we turn this into essentially a stack machine, which is where the name Postcard-forth came from. And of our stack machine, or our interpreter, if you want to call it that, the input is the list of offsets and functions. So it's got essentially a to-do list of, okay, for each of these offsets for serialization, I need to take my base pointer, increment it by this much, and then call this function with that base pointer. And that function's going to know that it's expecting a pointer to a U8, so it's going to cast that void star or star const unit type back to the correct type and go, okay, that's a pointer to U8, read that, and encode it onto the wire. And that becomes our output, is just some kind of stream of serialized bytes. So it could be to a vec, it could be filling up a slice and then keeping track of how many you've written to that, or however you'd like to, but you get some kind of stream output primitive that you can use there. As I mentioned, this is basically an interpreter. We're interpreting the definition that we generated at compile time of all these fields and walking through that as if we were a Python interpreter or something like that, and our output just goes to the output stream. And forth, as an interpreter, says that data is code. One of the lists says code is data, and forth says the opposite, data is code. You can interpret any chunk of data as if it was code if you write code that can handle that. And that's exactly what we're doing here, is we're generating data instead of code at compile time, and then we write one interpreter that knows how to turn that data into data on the wire.
And I'm going to stop you there. Again, it's interesting because you went the exact opposite direction that I did. I also was like, well, I like Serde, but then the direction I was in, instead of doing the stack manually, I took the one stable Rust feature that generates a state machine for you, which is async functions, and I just did that. And that also solves the infinite recursion problem. But I'll present my take on it in a different episode. It's so interesting. You were like, let's do everything manually. I bet you don't even have code gen for your thing. I bet you've been writing those arrays manually, haven't you?
I did it first. Now I have a macro that does that. So I actually do have a version of this that works. Not everything works perfectly and only for some subset of works, but...
Isn't that against the rules of the podcast? Like, we can only present far out ideas that don't actually work?
I've been talking about Postcard-RPC, and Postcard-RPC exists. It's just something I keep changing.
So you keep claiming. All I see is like screenshots on Blue Sky. I don't know. I'll believe it when I see it.
It counts. So why is this good? One good thing is that there's only ever one serialization, deserialization machine. It doesn't get monomorphized for every single version of that. And Serde generates a very simple, easy to optimize chunk of code, but it generates one of those for everything. And in this, there is just one, the VM, that handles whatever data that you throw at it. And it is an explicit stack machine. You can have a stack in there, and as you traverse down the stack, you can say, oh, my max stack is 16, and if you ever try to push a 17th item onto the stack, the stack machine just goes, oops, out of stack. Serialization failed, which is a challenge sometimes, particularly when you're deserializing unbounded types. If you're deserializing a vec of enums that can contain a vec of enums that can contain, you can get sort of like that zip bomb problem when it comes to deserialization. And Serde JSON has some workarounds for that, and Serde itself has some workarounds for that, where it'll try not to allocate too much. It's a hard problem when you don't have bounded types when you are doing recursion, because the compiler has no idea what your stack limit is at your runtime, and it will just go until the operating system says fail, dead, and then your program ends, which is not a very good denial of service protection.
And if you just have like one very, very large type, they have to be cautious because they don't know how much stack one function will take. If it has big locals, then it's a fat frame. So they have to leave sort of a red zone of like, okay, we assume that we can call at least one more level recursion. Everything related to stack bounding in Serde is a huge hack, including the one that lets you technically recurse infinitely, called Stacker. I don't know if you were going to mention that. Yeah.
Oh, yeah.
It was just like resize the stack and swap to it, as far as I know.
Yeah. I've seen that. I have no idea how it works.
It's terrifying. It's just straight up changing the stack pointer.
And embedded, if you run out of stack, you just run into your global variables and start corrupting them.
Yeah. No, it's like detecting you're going to run out of stack, so making a bigger stack, switching to it, and then I guess switching back before you unwind. I'm just terrified what happens if you switch stacks and then you recurse back. I don't know, you something set jump, long jump, like something's...
No idea.
Somehow go-tos into C code. I don't know how that would work, but that's terrifying.
So like I said, I have a version of this that at least for some values of works. And the interesting thing is that there's a really good serialization and deserialization benchmark written by the author of Archive. It's called the Rust-C serialization benchmark or something like that. It's something that I've used a lot and was very helpful for tuning Postcard, in that it has a couple of fairly large data sets for log files and structured save files from Minecraft and then tessellation things. It exercises a pretty good set of what Serde can do, and it's used as sort of a semi-objective benchmark between different formats, both in size as well as speed. But I managed to get just enough of Postcard-forth working so that I could implement the same test sets from this benchmark on this, and then compare it against Postcard with Serde versus Postcard-forth. And so these are the 4 different benchmarks, and on all but one of the serialized benchmarks, these are the relative ones, but if you go to the repo, there's also the objective ones. In the first run, regular Postcard is 67% of the speed of Postcard-forth. In the second test, Postcard is faster, and so Postcard-forth is only 84% of the fastest. But in the other 2, Postcard-forth is 100% and Postcard is 67%. Basically, it beats it by like 25 to 50% on serialization, although it does lose by 15% in one of the 4 tests. And then on deserialization, it's between 10 and 50% of the runtime of the other ones. Of this very limited test set, on 7 of 8 tests, it's faster than Postcard with Serde, and in the one that it's slower, it's only a little bit slower.
That is impressive. I've had this question in mind. You had pointers to functions. Are those only for Postcard? How would you make that work for more formats? Would you just derive different tables?
Yeah, that's a good question. I wouldn't.
Okay, cool. Just checking. You know I had to ask.
Yeah, it's very reasonable. And this is that like cheating by doing less.
Yeah.
I'm cheating by only supporting one format that I know the qualities of in and out. So I know Postcard can run through this. You maybe could make it work with JSON and things like that, and that would be interesting, but that's not something I've tried to do. Maybe it could be possible by just replacing essentially the set of standard functions, but it would be much more invasive than it would in Serde, for sure.
Yeah.
Because it's not built with that degree of freedom in mind.
I feel like it's a fair comparison, though, because Serde is uncompromising in terms of performance. It's like we will monomorphize and inline all the things.
Yeah.
We're trying to be as fast as possible, even if you pay in compile time. So there's just no way to opt out of that.
Yeah. And the other thing that's very relevant for me, especially for embedded, is that initial testing shows that it's usually smaller, both in the amount of code that you generate and the actual binary size.
Usually? What do you mean usually?
I say usually. Actually, in all my tests, it was smaller and faster, but you know.
Exactly. How could it ever be?
It's not an exhaustive test, lies, damn lies, and benchmarks.
True.
To control for this, I wrote a code generation tool that would generate types that were arbitrarily deeply nested, so they would reference each other and stuff like that. And then I would build an embedded binary. Because it's no standard, I can control what goes into it much more, which means I can have the baseline where I do no serialization and deserialization. And then I just have a format that reads data in from the PC, deserializes it, and then reserializes it. I didn't actually exercise it. I can see what the real code size is because I know nothing's being optimized out because it's reading in from the PC, so it can't assume that anything can be optimized out. My baseline firmware image that does nothing but I think say hello world and read data from the PC is something like 10 kilobytes, and the whole project is 53 lines of code when I expand it. I've tweaked Postcard-forth because I was trying to figure out, is it better to do this or this? But in most of the cases, for example, just the baseline Postcard Serde and Postcard-forth for 512 of these nested data types that might call each other. The compiled code size for Serde was 640,000 bytes, and the compiled code size for Postcard-forth was 395,000 bytes, so like 2/3 of the size.
Yeah.
The actual source code in the file, including those types that I generated, was about 10,000 lines of code. Serde turned that into 181,000 lines of code, and Postcard-forth turned that into 60,000 lines of code. So again, about 1/3 of the size. And then when it comes to compile time, I did measure both the total compilation time and just of this crate using cargo timings. And the difference in that compilation time is about 12 seconds for Postcard-forth and about 26 seconds for Postcard Serde. And this is like a mean test of generating 512 types where most of them include 7 or 8 of different ones. It's about as bad as it can get. But in this stress test, the sizes are typically about 1/3 of generated code, about 2/3 of the actual compiled binary size after optimizations. And it seems to be fairly consistent when I run it against a bunch of different generated types.
Did you go back to your customer and have them try Postcard-forth?
No. They do not need this. They're doing this on a desktop.
The public wants to know, James.
Yeah, I don't experiment everything in my customers unless it's really good. We're still on the positives. For deserialization, it'd be very easy to do this in place, because if we wanted to deserialize, we could have that base pointer just be a maybe uninit in the return location, and then use that as the pointer that we walk through for deserialization. It is built to be done in place,
right.
So there are never stack copies because everything is either done from the source or to the destination. So why is this not good? Now we're getting to the red words on the slide. It's another crate that requires a derived trait for every type. Unless we get reflection in Rust, there's no way to get these offsets and map them to a pointer for every type. If we get reflection, maybe this won't be a downside, but we don't, which means this is another trait that you have to PR to all of your favorite types like Chrono or an algebra or whatever, where you want them to conditionally implement some another derived type. Serde is great because the whole ecosystem uses it. So if it doesn't implement Serde already, pretty much everyone knows what it is, and they're going to just hit merge on that PR anyway. Without mentioning all of the type erased void star pointers, the engine itself for doing this serialization or deserialization is wildly unsafe. I think it could be done correctly and you could test it with Miri and you could do that, but it's essentially like a raw scripting interpreter that you're plugging into your program, and if I get something wrong, then it'll do out of bound writes and do terrible things. Serde has the benefit, I think, almost entirely safe code. It might be entirely safe code because it's just generating very simple Rust code that optimizes very well. This is generating not that. It is doing pointer casting, it is doing additions to pointers and reinterpreting them. It's doing all the nasty tricks that are fun to look at, but when I say it's wildly unsafe, it is wildly unsafe. And the other thing is that manually implementing these serialization and deserializing traits is wildly unsafe. If you have the derived macro do it and it gets the offset of correctly and things like that, totally fine. It will work as long as there's no bugs in the derived macro. If someone tries to manually implement that, like they can manually implement Serde today, you could just put an offset of 1,000,000 and then you're walking off into some other heap thing or you segfault. It is like a designed exploit in a box. I don't know how I could design it worse to be exploitable. You know what I mean?
I mean, that's why we have unsafe traits, right?
Yeah, it would be an unsafe trait for sure. We also still need some code to get to data model types. You need some monomorphization. Like I mentioned way earlier, a hash set gets represented as an array on the wire, but there's no like slice inside of the hash set. We would need to do something to go to an iterator to then each element and things like that. So there might still be some recursion or function calls or some kind of monomorphization that's required to get you to that data type.
Right. What about arrays? How do arrays work with Postcard-forth?
Right now, I think I just have a function that takes them as a slice or something like that. Like there's still some cheating for sure in there.
Yeah, okay.
But in my test, I only use like strings and vecs of U8s and things like that.
Mm-hmm.
They end up becoming that. Yeah, especially for iterators. Basically things that you can't deref to a data model type. And for that in-place deserialization, we need a whole new RFC because there's today no way to set the discriminant unsafely for an enum. So right now, the only way to deserialize an enum would be to deserialize it onto the stack and then copy it to the destination. I have an RFC up to change that, but it's an RFC. It hasn't even started to be implemented yet.
Yeah, you're the one who wrote it up. When did you? Last week.
Yeah, so it comes out of this. I have a blog post a while back, and it was while I was doing this is I realized there was no way to do that for enums. I could do all the spooky stuff for structs and raw data types, but enums, you have to make them on the stack and then copy them. And that's why that perf table had like a no enums field, because I was trying to figure out how bad that was when compared to other types. And it's not quite a linear program either. So when I say that it's a program and you just run top to bottom, turns out, no, you need control flow too, because even just data types are complex programs. For enums, you need branching. You are only serializing one of possible choices or only deserializing one of possible choices. And we need loops because you have slices and iters and you have to go through them, and you're not going to inline every possible length of every possible type. It really is a whole interpreter that not just needs control flow.
You're going to have to design your own bytecode, and then the array is going to be like type of instruction and then a few operands, and it could be a function address, it could be something else.
Yeah.
Is that even Rust at this point? Does that count as Rust?
Forth has some ways that you handle that, but that's probably a whole talk for another time. So then the question is it worth it? It is wildly unsafe, it is questionably implementable today, and you'll still end up with, in some metrics, a much worse version of Serde, despite being faster and smaller and things like that. And really the answer is I have no idea yet, but it was something that I spent a lot of time on, and I thought you might find interesting. So
I sure do.
We'll see if some calculus changes with something that makes it really worth it.
I mean, this is a perfect setup for my take on another Serde, which we don't have time for today, but this is so fun. You took all the other choices. I'm so glad we're doing this together, James.
I'm excited to see yours now, because you've talked about yours, I think, a bit more publicly.
Yeah, but I wanted to make sure it was useful before I actually talked about it. I never knew when the time was right.
Oh, I want the opposite. This episode is sponsored by Codecrafters. Codecrafters is a service for learning programming skills by doing. Codecrafters offers a curated list of exercises for learning programming languages like Rust or learning skills like building an interpreter. Instead of just following a tutorial, you can instead clone a repo that contains all of the boilerplate already and make progress by running tests and pushing commits that are checked by the server, allowing you to move on to the next step. If you enjoy learning by doing, sign up today using the link at sdr-podcast.com/codecrafters or use the link in the show notes to start your free trial. If you decide to upgrade, you'll get a discount and a portion of the sale will support this podcast. That's sdr-podcast.com/codecrafters. Thanks to Codecrafters for sponsoring this episode.